Hello and welcome back to Thermodynamics, and this is now the last lesson for this course. So we have now discussed about the efficiency of Carnot engines and the coefficient of performance of Carnot refrigerators, wherein we found out that they only depend on the temperature difference between the temperature of the hot region and the temperature of the colder region, or the hot reservoir and the cold reservoir. So we have found out that we can maximize the efficiency of a Carnot engine by maximizing this temperature difference. And we also have found out that we can maximize the coefficient of performance of a refrigerator or an air conditioner by minimizing the temperature difference between TH and TC. So in this last lesson, we will now be talking about how is the second law of thermodynamics, how does it fit in the Carnot cycle or Carnot engine and Carnot refrigerator picture. So this is now what we call the Carnot statement of the second law of thermodynamics. So it is impossible for any heat engine to be more efficient than a Carnot engine, because again, as we have mentioned before, the Carnot engine is the ideal or the perfect engine. There is no engine that is more efficient than this engine. In terms of the refrigerator statement, the Carnot statement says that it is impossible for any refrigerator to have a greater coefficient of performance than a Carnot refrigerator. So again, the Carnot engine and the Carnot refrigerator are the perfect engine and the perfect refrigerator. There's no engine, there's no real engine that has more efficiency than a Carnot engine or has a more coefficient of performance than a Carnot refrigerator. So real engines and real refrigerators actually just use the concept of the Carnot engine and refrigerator as a guide in manufacturing an engine and a refrigerator. So making the temperature as large as possible for engines and as small as possible for refrigerators. So in this example, in this picture, you have a jet engine. So to maximize the efficiency of the jet engine, it is the temperature inside the jet engine is made as high as possible. So the temperature inside is made as high as possible, as higher as compared to the outside of the engine, which is just the environment or the air, so that it can have a maximum thermal efficiency. So sometimes they use exotic ceramic materials that can withstand temperatures of excess of 1000 degrees Celsius without melting or becoming soft in order to achieve the highest possible temperature inside this engine. So another interpretation of the Carnot statement of the second law of thermodynamics is that all Carnot engines or all Carnot refrigerators operating at the same temperatures will have the same efficiency or will have the same coefficient of performance regardless of the nature of the working substance. So if you have found out in our equations before, in the previous lesson on the Carnot engines and Carnot refrigerators, the efficiencies and performance only depends on the temperature, TH and TC. It doesn't depend on the nature of the working substance, whether it's air, whether it's gasoline, whether it's freon. It doesn't depend on the nature of the working substance, but only on the temperature difference. That's actually what matters. The temperature difference between the hot and cold reservoir. It should be as large as possible for an engine and as small as possible for an ideal refrigerator. So let's now try to calculate the work done in a Carnot cycle. So this is for a Carnot engine, and the reverse of this cycle, the reverse of the arrows again, is a Carnot refrigerator. So the work done from A to B is an isothermal expansion. So isothermal expansion, we have mentioned this before in chapter 3, how to calculate the work done in an isothermal process. It's actually just equal to QH, where it's nRT ln of the final volume over the initial volume. In this case, the final volume is B, the initial volume is VA. So that one. In B2C, B2C is an adiabatic expansion. Isothermal process means the change in internal energy is zero, meaning the work done from A to B is just equal to the heat absorbed in A to B. That's what it means by an isothermal process. Work is just equal to heat because the change in internal energy is zero. If you will recall, the change in internal energy, U, is Q minus the work. The heat absorbed minus the work done by the system. So in this case, if zero on change in internal energy, then Q is equal to the work. So Q is equal to the work in A to B, in an isothermal process. In an adiabatic process, there's no heat involved, so Q is equal to zero, meaning the work done in an adiabatic expansion from B to C is just equal to the negative change in internal energy, where for an ideal gas, the change in internal energy depends on temperature, NCV. So since this is negative change, so this will now be initial temperature minus the final temperature. In this case, the initial temperature, which is at point B, is TH, and the final temperature at point C is TC. So take note, this is negative change. The regular change is final minus initial. But this is the negative change, the opposite or the reverse of a change. Then so this will be initial minus final. So the initial is TH, the final temperature is TC. So I hope that's very clear. So in C to D, it's another isothermal process. So it will be nRT, the temperature in this case is TC, ln of the final volume, which is VD, minus the over the initial volume, which is VC, the volume at state C. And the last process is from D to A, an adiabatic, C to D is an adiabatic, isothermal compression, and D to A is an adiabatic compression. So again, it's still negative change. So final temperature at point A, which is it's negative change. So initial minus final. Negative change means initial minus final. So initial temperature is TC at point D. Final temperature at point A is TH. So again, this is an isotherm. So all temperatures along this blue curve here is the same. It's an isotherm, constant temperature curve. So these are the work done in a Carnot cycle. So you will notice that in a Carnot cycle, the ratio between the volume VB over VA is just equal to the ratio of the volume VC over VD. Okay. So let's now try to expand the efficiency of a Carnot engine. So we know that originally, this is the original equation for the efficiency of a heat engine, any heat engine. It's work over QH, where work is QH plus QC. Therefore, if you write this, you can write this in terms as of 1 plus QC over QH. But when we define the Carnot engine thermal efficiency, it's actually equal to 1 minus TC over TH. And comparing these two equations, the equation for the efficiency for any heat engine and the equation for a Carnot engine, take note that this is equal because a Carnot engine is still a heat engine. So a Carnot engine is a heat engine. All Carnot engines are heat engines, but not all heat engines are Carnot engines. Take note that, huh? So all Carnot engines are heat engines, but not all heat engines are Carnot engines. So we can compare these two and equate them. So we can actually use the idea of the Carnot engine to define the Kelvin temperature scale. So TC over TH is just equal to negative QC over QH, or QC over QH is equal to negative TC over TH. So you'll notice that from this equation, it's independent of the working substance, whether it's an ideal gas or not, whether it's a liquid, a gas, or any fluid. So uh, the Carnot, the concept of the Carnot cycle and the Carnot engine and the Carnot refrigerator in general uh, can actually be used to define the Kelvin temperature scale. So this is one way to define the Kelvin temperature scale. So this relationship between the temperatures of the reservoir and the heat absorbs, QCQH, applies to both a Carnot engine and a Carnot refrigerator. So they can be used both to define, they can both be used to define the Kelvin temperature scale. Okay, let's have an example. So let's try to analyze a Carnot cycle. So this is a Carnot cycle. So it's in the form of an engine. So this cycle, these original arrows are for an engine. Suppose you have 0.200 moles of an ideal diatomic gas. So if it's a diatomic gas, it's gamma. Its heat capacity ratio is 1.4. And it undergoes a Carnot cycle between 500 Kelvin and 300 Kelvin. So TH here, our TH here is 500 Kelvin. Our TC is 300 Kelvin. Starting at a pressure of PA, so the pressure at point A, so this pressure here at point A is 10 times 10 to the 5 pascals. The volume doubled during the isothermal expansion. So in this isothermal expansion from A to B, the volume doubles. So the volume at point B is actually double the volume at point A. And for the first question, we are asked to find the pressure and volume at points A, B, C, and D. So pressure and volume at points A, B, C, and D. So you actually know the pressure at point A. That is actually given. So the rest we need to solve. So let's try first solving for letter A. The pressure and volume at points A, B, C, and D. So for this problem, we will use the concepts of the ideal gas, which we have discussed in Unit 2. I will also need the concepts of the first law of thermodynamics and the different kinds of thermodynamic processes which are found in Unit 3. So basically, you can treat this problem as a completos recados na problem. A problem that is expected of the finale of this course. So it will now use all of the concepts that we have discussed starting from Unit 1, Unit 2, Unit 3 until now Unit 4. Okay, for letter A, at point A, so at this state, at state A, the pressure there is given 10 times 10 to the 5. So how do we find the volume? So we are given the pressure. So to solve for the volume, we just use the ideal gas equation. So PV is equal to nRT. So PA times VA is equal to nRTA, the temperature at point A. Where the temperature at point A is actually along the isotherm TH, which is 500 Kelvin. So we can now solve for the volume at point A. Substituting all the values, and we get a unit in cubic meters or meter cube, the SI unit for volume. So 8.31 times 10 to negative 4 cubic meters. So we are now done with point A. So let's now go to point B. We can solve for the volume first at point B because it says here that the volume at point B is just double the volume at point A. So we already have solved for the volume at point A, so we just multiply that by 2 to get the volume at point B. So we now know the volume at point B. How do we solve for the pressure at point B? Again, we use the ideal gas law. So P, pressure at point B, volume at point B is equal to nRT, temperature at point B. So the temperature at point B is just the same temperature at point A. It's still TH, the higher temperature region, 500 Kelvin. So substitute all of that and you will get 5 times 10 to the 5 Pascal. That's the temperature, the volume and temperature, volume and pressure at point B. So let's now proceed to point C. Let's now try to find the pressure and volume at point C. By the way, you can also use this. You can also obtain this if you use Boyle's law. So P1V1 is equal to P2V2 because this is an isothermal process, constant temperature. So if temperature is constant, then pressure, the product of pressure and volume is constant. P1V1 is equal to P2V2, Boyle's law. Okay, let's now solve for the pressure and volume at point C. Okay, so this is an adiabatic process. So B to C is an adiabatic process. And the temperature and the volume in an adiabatic expansion are related using this equation. So you must recall this equation in your Unit 3 lessons. So TB, the temperature at point B, which is TH, VB to the gamma minus 1 is equal to the temperature at point C, which is the temperature of the cold region, T capital C, VC to the gamma minus 1. So we know the temperatures. We have already solved for the volume at point B. So we can now solve for the volume at point C. So it's just this one. And you will get a value of 59.6 times 10 to negative 4 cubic meters. So this is the volume at point C. So all we need to do now is to solve for the pressure at point C. So again, to solve for the pressure at point C, we use the ideal gas law since we already know the volume and the temperature. And we can now solve for the pressure at point C, equal to 0.837 times 10 to the 5 pascals. Now, the last point, point D. So at point D, again, point D to point A is an adiabatic compression. Again, we use the same equation, relation for the temperature at point D and the temperature at point A. The temperature at point D is TC. The temperature at point A is TH, the higher temperature region. And solve for VD. We already know VA. TH and TC are given, so the only unknown here is VD, the volume at point D. And we get a value of 29.8 times 10 to negative 4 cubic meters. And for the pressure, again, at point D, we use the ideal gas law since we already know the temperature, the volume at point D. So we can now solve for the pressure at point D equal to 1.67 times 10 to the 5 pascals. Okay, we're done with letter A. It's a very long problem. Okay, for letter B, we are now asked to find the heat absorbed or released, the work done on or by the system, and the change in internal energy for each step and for the entire cycle. So we need to find the Q, the heat, the work, and the change in internal energy for every process. For A to B, we have 4 processes here. A to B, B to C, C to D, D to A. So we need to solve 4 values of Q, W, and change in internal energy, and for the entire cycle. Okay, so let's start with A to B, isothermal expansion. So what is QH? So isothermal expansion, meaning the change in internal energy is 0, meaning QH is just equal to the work. So QH is just equal to the work, so the change in internal energy is 0. And the heat absorbed in the process A to B is just equal to QH, in this case, this one. And it's also equal to the work done in A to B. So the work done in A to B is just nRTH ln of VB over VA. We have already solved VB, VA. And it's 576 joules. So take note, for every process, we need to solve for the heat absorbed, the work done, and the change in internal energy. In this case, the change in internal energy from A to B is 0. And the work done in A to B and the heat absorbed in the process A to B are the same. They're both 576 joules. Okay, that's one down. A to B is already done. Let's now go from B to C. Adiabatic expansion. Adiabatic expansion means there is no heat involved. So meaning the change in internal energy is just equal to the negative of the work done. Or the work done from C to D is just the negative of the change in internal energy. So the work done is just equal to the negative change in internal energy. So initial temperature, temperature at point B, which is TH, minus the temperature at point C, which is TC. So for a diatomic gas, CV is approximately 5 halves R, approximately 20.8 joules per mole Kelvin. So that means that the work done from B to C is 832 joules. And the change in internal energy is negative 832 joules. Take note, we are trying to find three quantities here. The Q is 0, the work is 832 joules, the change in internal energy is negative 832 joules. So from C to D, another isothermal process. It's an isothermal compression. So change in internal energy is 0, meaning the heat is just equal to the work. So, and those are equal to negative 346 joules. So in this case, heat is released by the system, QC. So heat is released by your Carnot engine. And the work done is also negative. So meaning work is done on the, in this case, in this process, work is done on the system. Okay, for the last process, D2A, adiabatic compression. So again, zero heat, no heat involved. So the work done from D2A is just the negative change in internal energy from D2A. So initial minus final. So we get the work to be equal to negative 832 joules, meaning the change in internal energy is the negative of the work. So it's positive 832 joules. So the work, the change in internal energy is positive 832 joules. So this is the summary now. In the process A to B, this is the heat, the work, and the change in internal energy is 0. So take note, change in internal energy is Q minus the work. So since Q and work is equal, 0 change in internal energy. It's isothermal process. So adiabatic process, 0 heat. So meaning the work is just the negative of the change in internal energy, and so on. So you will notice that if you add all of the heat in the total process and add all of the work, it's actually equal to each other. And the total change in internal energy of the system is 0 because this is a cyclic process. Take note, if a process returns to its original state, so it starts from A to B to C to D and then back to A, so that's a cyclic process. So you should expect that the change in internal energy of the whole cycle should be equal to 0. So it's a reversible cyclic process. So QH here is 576 joules, and QC is negative 346 joules. And QH plus QC, of course, is 230 joules. Okay. The last problem, letter C. So this is a very long problem. Find the efficiency in two ways. Directly from the results of part B and using the temperatures of the reservoir. So we now have to solve for the efficiency of this engine in two ways. Using the results that we have in part B or directly using the formula, using the temperatures of the reservoir. Okay, using part B, we found out that QH is 576 joules and the work is 230 joules. Therefore, the efficiency is just work output over QH heat input, and you will get an efficiency of 0.4 or 40%. So that's the first way, using the result that we have in part B. But we can also solve for the efficiency, since this is a Carnot engine. We can, again, these two formulas can apply to a Carnot engine. But again, not all heat engines are Carnot engine, but all Carnot engines are heat engines. So you can also use this formula since this is a Carnot engine. So 1 minus 300 Kelvin over 500 Kelvin, 1 minus Tc over Th, and we will get the same result of 0.4 or 40% efficiency. So that's it. So that is the finale, the last problem for this course. So I hope you have learned something. So the final problem is actually a combination of all the concepts from Unit 1 to Unit 4. So I hope you try to understand the last problem. It's very fast for you. So you pause the video and reflect what happened there in my solution. So I hope you learned something in the course, and I hope I will not see you in the next semester. I hope you pass the course, and I hope you will get good score in your final exam. So good luck on your final exam, and I hope you will pass the course. So thank you for listening, and God bless.